Thanks for having me. So just as a little bit of an overview, this is I would say category theory adjacent at best, but I'm kind of working with formal systems design for more high school level education. I have a 2-year grant it's an exploratory grant, so we're just looking at different approaches to algebra and ways of communicating them through video games. And I thought in particular this project work might be interesting to Topos because I know Topos is trying to create new kinds of tools and new formalisms like Cat Lab. And I think more generally in this space there's things like the adoption curve for functional programming or proof assistance. And I think one thing that's interesting about these alternative formal systems is that they're offering kind of a tricky offering because they're not like substitute goods that make your life easier. They actually make your life worse for a little while as you kind of learn the abstractions and then make your life better later. So the value proposition, how do you goose adoption? How do you first attract people to your system in the first place? So I'm trying something with video games. And I thought that example might be worth investigating. I also have, at the end, I'll mention, I think I have some questions that I think might have a good categorical point of view. So I'm definitely interested if anyone wants to chat more about this and can help me understand what I'm doing from more of a categorical perspective. That would be helpful. Okay, so I'm Paul. I'm doing a project called the Digital Abacus, and I want to say a little bit about my background and what led me to this work. So for about 13 years, I was actually a hands-on science exhibit designer at a science museum in San Francisco called the Exploratorium, which is this giant cavernous space with over 500 homemade hands-on science exhibits. These are all kind of focusing on science, art, and human perception, and everything is made in the workshop at the Exploratorium. And we have kind of an unusual practice there, which is that in a lot of science museums, there's a team of pedagogues who design whole exhibitions, whereas we are really more of an artisanal shop. Each person kind of carries an exhibit from first cardboard prototype to final, hardened floor exhibit. So each one is an individual's kind of work of art, and I really think that shows in the quality of the collection. So in 2003, I was hired as a junior exhibit developer, and I got to spend a long time as an apprentice in this really interesting form of creating sort of educational products. I really specialized in math exhibits, so these are some things I made over time. This was a 10-foot tall climbing structure modeled after a triply periodic minimal surface called the gyroid. It's one of the most confusing things to climb around inside of. I really love that one. This was a kinetic sculpture. I worked with an artist. I designed the internal gearing mechanism, and he designed this pattern based on Fibonacci phyllotaxis. So these are the kinds of things we made over time. Sort of the template for an exhibit. So here's an exhibit. This is called Hot Pile. It's a big pile of compost. And every exhibit is built around a natural phenomenon. So it's never my invention, right? It's resonance, diffraction, bacteria is digesting the compost and creating heat. It's, there's a natural phenomenon of warmth inside the middle of that pile of compost. So what we do is we supply people with big blue gloves, and they can stick their hands into the compost and feel have a direct experience of this natural phenomenon. So that's the user interface. And all we're doing is finding natural phenomena and building custom user interfaces such that the person can come up to this and take control of the situation and carry out some kind of interrogative engagement with that natural phenomenon. And this design of user interfaces turns out to be a lot trickier than you might think. Something that happened to me early on in my career, I had a kiosk for an audio exhibit, and I needed people to put on these headphones. And when we were testing it, we found that almost half the people just didn't pick up the headphones. So we're gotta fix that. So we made a little arrow pointing at them. And then maybe 60% of the people found it. And then we updated what was on screen saying, get the headphones. And then 75% of the people, and you'd color these bright orange. And you're kind of fighting this game at the margins. And then at some point it occurs to you, you're there's literally, I'm in charge of this whole situation. There's no reason they have to be off to the side like that. I can just put a post on there and have them dangling in front. And now 100% of the people use it correctly, and we don't have to waste label space and other things telling them how to use the bad design. And this is kind of a simple example, but the beauty of being an exhibit developer is that you kind of get to learn this lesson over and over again in increasingly intricate ways. And this becomes sort of the part of the design vocabulary of the floor. So if you go around on the Exploratorium floor, you'll see that exhibits that have headphones tend to have them dangling, because we find that looks to be the most effective way of just getting people to effortlessly use the exhibit correctly. So for example, this is one of the last exhibits I made there. This is a 12-foot long poster that has the first 3 million digits of pi, and it has a little iPad on it so you can look up your phone number or your birthday and then slide this microscope over and look for it and actually see your image in this natural constant. And the idea is it takes a minute to come up with that idea, but it took almost 6 months to make this because everything about the first draft is wrong. It's got to be low enough that a kid standing on a stool can get to the top, but not so short that an adult has to lie down. You know, how big should these blocks of searchable numbers be? What are like color blindness safe color choices? Everything about this is a hard-fought iterative battle to get it to the point where you've just sanded down all the speed bumps, all the barriers to learning, and you can tell that it's working when people effortlessly get the result you want and get excited and then want to find out what's the longest string of 9s, or, you know, like the point when they take over and start having questions of their own is like the goal you're working towards with these exhibits. So I did this for many years, and basically what I learned is that in a sense we're not really trying to teach people things in the sense of like empirical knowledge. There's nothing to learn about pi at that exhibit. What we're trying to do is just get people asking questions. Like, we are interested in putting them in a situation where they're the ones in control, and that we are trying to, in some sense, adjust their sense of self or their affect, that they are the kind of person who can figure something out and that it is a pleasure to do so. And that getting this to happen is very little about inspiration. It's almost all about user interface design. So I think of myself as an educator as someone who is not trying to provide instruction or give information, but is just trying to facilitate other people in asking their own questions. I love math, and for the purposes of asking questions, knowing math is a really powerful kind of proficiency to have. So this is an exhibit called Bouncing Ball. It's actually an acoustic exhibit. This ball is making a noise every time it bounces, and eventually it decays down to a point where those percussive noises become like a continuous tone. And you can do things like polish this plate and it'll bounce longer. You can affect it in different ways. But a person with mathematical proficiency can ask a lot of questions that a normal user can't. Like, they can figure out how many times the ball bounced, or they can predict how long it would bounce for if we dropped it from twice as high, or like, what is the coefficient of restitution need to get down to for the ball to bounce for 3 minutes? These are all questions a mathematically proficient person can answer. The problem is that when asking and answering those questions, this is what it looks like. We've done like mathematical analysis of all these exhibits, and it's just kind of a nightmare to figure stuff out. Just the procedural overhead in figuring these things out is a lot more than you could teach anyone in a museum setting or really ask of anyone. And after about 15 years, I started to be like, you know, in a funny way, like this written symbolic notation it's just a user interface for the number system, right? It's something we've invented, and as someone who thinks of education through user interface design, I'm like, this is a really crappy interface. And, you know, not to belabor everything that's wrong with it, but like, you know, what I started to dream of is that, you know, if you're having, like, an exhibit developer is dealing with a bad interface, what they do is throw that away and replace it with something else which doesn't have those problems. So this is kind of what I was interested in. It's not so much a teaching tool, but a tool. Something that you could use to ask and answer number questions that could be in the middle of like exploring exhibits or doing activities, or something that was an alternative to written mathematics. And the analogy that I kind of attach myself to is like, this kind of thing has happened before, right? For the purposes of arithmetic, people used to use Abacus or written notation. There's even prints of like an abacist in a race with an algorist doing this in these two different styles. And in the long run, eventually writing one out, this is a much better, more flexible, more portable medium, and you can extend it to algebra and calculus and all the rest of mathematics. But what I kind of became curious about in a very novice way was like, you know, something's fundamentally different now, which is that we have computers. And it's not just that we have computers, it's that civilians can take for granted a general computational layer that is available to them at all times. And my thought was like, well, does this new medium allow for another change, like another mode switch of this sort? Like, is there some computationally based representation system that can give us something new. And we use computers to do math. Like I can type this into Wolfram Alpha, but I'm typing it in using text, using a static medium. So I'm really communicating with the computer using a language designed for pencil and paper, and probably like adapted to the constraints of pencil and paper. So the question I started to have on my mind is like, what else could we get? And at the time I had literally no idea how to even start to ask that question. But I started a kind of R&D project at the Exploratorium, which I called the Digital Abacus, and the goal was to look at other representation systems for numbers and kind of see if these could be valuable for inquiry-based pedagogy in some way. So I kind of worked on that from the beginning of 2017 till about the end of 2019. And to skip over a lot of trial and error, one of the main things was that eventually I realized there was such a thing as programming language theory. And what I really wanted was like a domain-specific language that could do some chunk of conventional algebra or something like that. I'd actually made a bunch of little calculators and realized there were kind of two ways of doing arithmetic, and then later I learned that was what's called curried and uncurried. So in like my gonzo way, I had figured out a lot of things that turned out to have names and fit into like a general theory. So algebra is about functions, and there were these things called functional programming languages and relational programming languages, declarativeness. I'm like, there's a lot of good ideas here that could be brought directly to approaches to algebra. And what was really exciting to me as I got through this was that I realized you get this very different style of calculation. It could feel very different to carry out a calculation. In particular, I'm going to make the claim that written mathematics is strongly imperative, and the available systems we could implement on a computer could be more declarative, and that is actually an appealing possibility for a number of reasons. So anyway, at the end of all that, I had come up with a specification for two different visual interactive programming, domain-specific languages essentially for doing algebra. I have found that it's nice to have two, because when you tell people that you're reinventing algebra, you kind of give off sort of a crackpot vibe. So to say that I'm interested in alternatives, these are two examples, and this is the kind of thing that you can formally generate and play around with. I was a little bit unsure how much detail to go into with these, but basically, this one is this background is the complex plane, and what you have are geometric shapes that represent points that are additively related or multiplicatively related, and everything you build in this space corresponds to a complex function. I'm not going to talk, it's just a mouthful to talk about these, and I'm trying to give a kind of a quick overview. This one, I found that a lot of educators I talked to were a little bit intimidated by the complex number aspect, which wasn't super important. So I actually ended up making a more node-based thing, which is also run. These have the same underlying data structure, but this one's only showing the real numbers. And basically my claim about this is that in the same way that the abacus and the written form are equally good for doing arithmetic, this circuit system and this written system are equally good for solving for x. So what I thought I'd do here is let me show an example of an algebra problem and how it's solved in both of these systems, so I can kind of articulate what I think is different here and why it's interesting to me. So let's look at the question, what are two numbers which add up to 17 and multiply to 52? So the student doing this in writing is expected to know how to do this. The first step is they simply re-express this question in the formalism itself. So we've minted these terms x and y for our unknowns, and we've specified what their arithmetic relationship is. We can't act on two separate equations, so the next step is to solve one of these for y, substitute it into the other, work that out, and we get a quadratic equation, and then hopefully the student knows the quadratic formula and can plug in these coefficients, and then when they work that out, they get the answers down here. So this is an example of how an algebra problem is carried out on paper, and there's really three steps to this, right? In the first place, you just declare the question. There's nothing here except precisely what is present in the verbal description of this question. Then there's this solving step, which is a procedural step-by-step operation, and then at the end, an image of the answer has been generated. And all algebra, yes, Owen.
Do you mean multiply to 42?
Huh?
Do you mean multiply to 42?
Oh, does this, really?
Yeah.
Oh my gosh. Wait a minute. No, that's 52.
I see 42.
Are you kidding me?
Yeah,
Oh my God. Well, I don't actually know any math. That's interesting. Well, it's interesting because, well, okay, let me say what I was going to say, and then I'll fix these slides later.
That's not important.
No, that's a good catch. Thank you. I'm glad someone caught this in a safe place. But the point I'm trying to make is that this step is the major obstacle to an inquiry-based pedagogy, right? You can imagine doing an activity with a student and it comes up that they need to figure out the dimensions of a box, that they have enough material for the perimeter and enough material for the area. But then they got to stop with like open-ended self-guided inquiry and engage in this highly strict procedural operation in order to move to the next step of the yeah, David?
I was also involved because it's 13 times 4, not 14 times 3.
Oh, that's why. Okay, so I transposed this. I solved this problem using my tool, and then I think it's 13 and 4 works, right?
Yeah.
Okay, that's what's wrong.
Yeah.
You know what? Let me fix that right now. Oh wait, I can't. That's a video. Okay. But my point is simply that like this solving step is, first of all, it's distinct for every kind of, if I have a different kind of algebra problem, I'm going to need a totally different solving procedure, and it doesn't scale very well, right? If this problem gets much harder, the possibility of even solving it procedurally is going to become intractable. So this is kind of the part you want to get rid of. And my claim is that this part is an artifact of the static medium, right? If you're writing it down, there's no other way for the answer to get here except that you have some way of tricking yourself systematically into writing it. So let's solve the same problem using my reversible network node system. And what we're going to do is just do the same thing again. We're going to declare the problem in parts. So the first thing is we need 2 numbers. So numbers in this environment are, we don't have variables. What we have are these things, which are just these, they're essentially variable numbers. So I can slide back and forth to set these to anything I want. Next, I want them to add up to something. So I'll pull out an adder and plug them both into the adder. Right now, they don't add up to 17. We'll set that in a moment. The next thing is we want them to multiply to something, so we add kind of a multiplicative constraint. And then the thing with all of the main ingredient you need in order to emulate regular algebra is that all of these dependencies need to be essentially reversible, and reversible in a way that is compliant with composition. So I can, right now, I control 8 and 4, and the computer gives me 12 and 32, but I can actually turn that around. I can double click on this and route it backwards through the 4, and I can double click on that and route it backwards through the 8. And now I can no longer control 4 and 8, but I can specify what I want them to add up to and what I want them to multiply to. So now I can force these 2 numbers to add up to 17. And it back percolates through all of these, so apparently 14.8 and 2.2 are 2 numbers which meet these specifications. And then I can dial in my multiply to 52. And there's the right answer, 13 and 4, which actually points out a big problem with writing, is that it's very easy to make transcription errors and accidentally produce false statements, whereas it is impossible to produce false statements with this system, which is, again, like, essentially, if you didn't even know the question, you could look at this and figure out what it must have been. Clearly, whoever made this was trying to find 2 numbers that added up to 17 and multiplied out to 52. So there's almost this exact one-to-one correspondence between answered algebra questions and states of this system. And there are a bunch of other computational things about it that are nice. Like I could package this up and save it for any time I want to answer this question again, and it's compositional, so I can use it in a bigger network that's modeling something, a little bit more like bigger in scope and things like that. So I have a sense of like what the various use cases are for this kind of system, and I thought it could be very useful for inquiry-based pedagogy because of all those things, right? We have an imperative system that depends on step-by-step procedures. This is a lot more declarative in the sense that I can answer a question simply by declaring the specification, and it basically works. You're dealing with almost like an equilibrium system and dealing with constraints on that system. And in a way, it's like a query language for the numbers, which if your goal as an educator is to create tools that help people ask questions, you could not be more on the nose than changing it up in this way. So I had these systems, and in terms of looking for funding and thinking about how to deploy them, for a while I was thinking maybe we could put these in schools. It could be a supplementary material for algebra or something like that. And I increasingly became skeptical that this was going to work, or was really, it may be possible, but for a variety of reasons I was feeling like I maybe needed another idea about how I might deploy this in real life. About a year ago, I left the Exploratorium and I got a grant, and the theme of the grant is to say, well, can we use video games as a context where people get familiar with these systems and how to use them to answer questions? There is some precedent for this kind of thing. There are mathematical video games. A famous one is, this is called Dragon Box, and it's a puzzle game where you're trying to get this box by itself, but it's actually secretly algebra, and that when you get the box by itself, you've solved for x. And there was that little whirlpool that you could make disappear. And they introduced, there's nighttime and daytime dice, which will cancel to make one of those things that go away. And little by little, they increase the number of variables and the numbers on screen. And basically, after a while, you're solving a level is really solving an algebra problem that could probably stump a few adults. And I thought this was an interesting approach because it doesn't teach you anything about what any of this means. It is conceptually blank, but it has identified that the procedure of solving for x is itself a kind of puzzle game, and has simply manifested that game as a way to try and teach this. The word on this is that it doesn't transfer. You can totally beat this game and still have no idea how to solve problems on paper. The other critique I would say is that this is not terribly successful as a game. One of the advantages of making a good game is that people will choose to play it. There is an intrinsic motivation that comes from wanting to play a game that is well designed and beautiful. And while this addresses mathematical needs, it doesn't quite, I think, reach that criteria. So the kind of genre of video games that we're interested in this grant are what are called thinky puzzle games. It's a kind of a niche genre, but I just want to show a few of the sterling examples from this. There's this man, Alan Hazelden, is kind of a savant of this. This is an amazing game called Monsters Expedition, where you're this monster. You can knock down a tree to make a log, and a log can either roll continuously until it hits an obstacle, or you can tumble it, depending on which direction you push it. So this monster is trying to get over to this island. So it first knocks the tree over, pushes it against that rock, and then tumbles it that way, and it's free to go. It seems like a simple mechanic. This game is so insanely complicated and has so many elegant, beautiful, and it has over 500 levels. So they just got so much mileage out of such a simple mechanic, and it is just a pleasure to play with. Another great one in this category is called Baba is You. So you are this little character, Baba. You're in a landscape, but in the landscape are these sentences, and you can push stuff around. And so normally in a game like a wall will not let you walk through it. But in this case, it's only true because wall is stop is a sentence somewhere around here. So what Baba can do is, I can't get in there, so I break that sentence, and now it's no longer true. So what you're doing is actually manipulating the laws of the universe until you construct a goal that you can achieve. And this is, again, an unbelievably rich, you can't believe how meta it gets after a while. It's a beautiful game. One last one. This is called Patrick's Parabox. This one's relatively new, and it's a block pushing game where you're trying to get these into that position and this guy into that position. But you can see that he can't get around these things. So the game is based on this really lovely recursive mechanic where you actually dive inside of the blocks. And once again, this game is hundreds of levels that just get more and more mind-bending as you go on. So, I mean, these are games that are compelling for reasons that have almost nothing to do with any exterior learning. But this is a quote from Patrick Traynor of Patrick's Parabox. Puzzle games are doing some kind of pure mathematical-esque exploration of some little corner of the universe. The goal is to showcase the system and all its cool intricacies and let people have the same discoveries and joy that he had when exploring this himself. And I felt like that was the situation I was in. I had these systems I'd been messing with in my own imagination for a long time. I thought they could be really compelling. And the question was, well, could we build a well-made puzzle game around these things? So my first year of the grant was basically I worked with 7 or 8 different indie game developers, and we just did a bunch of like speed prototyping of different ideas around those 2 systems I showed you. So the linkages system, so this is the linkages system in action. It's on some level there is a there's an arithmetic expression with complex values that this represents, but abstractly looking at it, it's just rotating and scaling and dragging. So it's kind of lends itself to some geometric interactions. So we experimented with maze-like games or Tetris-like games, or this one where you build something and then put one node on a conveyor belt and then try and trace a target path in another. This one I was optimistic about, and I really had a hard time getting developers interested in it, and these games were kind of interesting, but it felt like not very deep. We got a lot more investigation of the circuit system, and my position on this was like it didn't need to be strictly the circuit system. I think I mostly just wanted to play with the ideas of node-based programming, where you have boxes and wires, and just the concept that number data is migrating from one place to another. And beyond that, I was willing to be pretty flexible in terms of whatever ideas the game developers came up with. So actually Patrick from Patrick's Parabox helped me make this one where you are a little blue square and you're trying to touch a white square and then touch a green square after that. And the thing you build in the game are these essentially node-based controllers and try and navigate through different environments. This one was a game where you build expressions to light up a grid of dots and try and make different patterns. So these were pretty fun, and they both explored some interesting ideas like time-based blocks, and this had a recursor, it had an iterative recursor thing, so you could do like recursive programming. We also made some where instead of using the node-based thing as a programming environment for something else, you were really just trying to build highways and pipelines for numbers. Yeah, these were 2 experiments where this one you have clusters of dots and they're getting filtered based on whether they're even or odd. We were just throwing a lot of spaghetti at the wall, just trying to find different things that might be compelling. In the end, we did end up making these are screenshots of the node programming environment, which is rooted in a style of programming called shader programming, which is essentially each pixel in the screen is given a copy of whatever code you make, and it uses its coordinates as an argument to the function, and that allows each pixel to generate a different color. And this is notoriously a difficult programming paradigm, so the developer thought this might be something that would have a niche audience. And this was, I think, got to the point where like it's on itch, it's a publicly available game. Like we succeeded at making something in the end of the year that was public facing. And we have working demos. So I know I keep showing this slide, but actually a year ago this was all like in my imagination and I was trying to explain it to all these developers. But we have, as a side project, actually implemented some popsicle sticks and cardboard quality versions of these, but they're good enough. They work well enough to at least like solve quadratic equations and things. So I can use them to at least demonstrate the systems I want to ultimately build. There's a lot of work in numerical methods that's going to need to be done in order to get these working the way I want, but we've also made some progress on that. So that was the work from this first year. What did I learn? I mean, the main thing is like I got to make 8 or 9 games. So I had no prior experience in game development, and they're similar in some ways, but in a lot of ways making a game is almost the opposite of making an exhibit, where the exhibit is meant to be sort of accommodating to the person doing the inquiry. A game is really, the conversation is about obscuring something and making an interesting pathway to overcome that obstacle. So it was very counterintuitive to me to make things that were intended to be difficult. So I got a great education in game development. And the other thing I learned is that games are hard. The convenient thing would have been if one of these games clearly like lent itself to a really interesting kind of puzzle experience. And my feeling is that if there are interesting games here, they're not right on the surface. And I think to the extent that we were successful, it was largely by compromising on these systems as language models for dealing with numbers. Shaderoo is a shader programming game. It has nothing to do with algebra. It doesn't have reversibility built into it and probably can't. After this first year, I'm coming into my second year now, and I'm trying to think if there's kind of a shift in emphasis or a course correction I can make. and then this is also where I'm sort of in the middle of figuring this out right now, so this is where the talk starts to degrade probably a little bit. But one of the things that kind of became clear to me in the spring was that like the reason something like the linkages system is interesting to me is because it gives you access to like complex analytic functions, which is a field I know to be beautiful. It is, you know, like the opportunities once you've absorbed the abstraction of this, I think are extraordinary. But after showing this to enough people and seeing how bored they look, I can see that there was an eye of the beholder problem for me, and that ultimately, like I had these languages which describe something beautiful, and I was trying to make games about the languages. So the new idea is essentially there's a variety of reasons to say, well, what if I just start with complex analytic functions as the playground and just start to make interactives here, and in the end those might justify the acquisition of this language later on. So, and then, yeah, the complex number system has something these other things don't, which is that it's like psychedelically weird and beautiful and rich and varied, right? For a year, I was going to these poor game developers with these 2 language models and being like, can you make my languages fun? Whereas now I feel like I have a whole bunch of different places to look and holes to dig to start looking for games. I was giving myself the summer to try and inventory as much complex analytic stuff as might serve as the foundation for some kind of game. And then I have about another 6 months to try and explore, make those prototypes in detail. And then a year from now, if we can come up with anything, I'm going to try and pitch like a production grant to do an actual commercial product for this. So just to, we're doing actually okay on time. This is what's known as a domain coloring graph, so I'll just explain. A complex function is a map from the complex number system to the complex number system, and the logic of this image is that each pixel is, first of all, a point in the complex plane. It has a coordinate, and that is sort of the domain of the function, and each pixel also is emitting a color, and that is also indexed by a complex number. So with this, the color represents the angle or the argument of the complex number, and then these contour lines kind of show you how the magnitude of the complex number changes over time. And the idea is that you build up to this by starting with the integers and then learning about negatives and then quotients and then reals and then complex numbers, and eventually you get to the point where you can interpret this. But you can also, kind of what I realized, you can start at this end too. I can say here's a alien skin, and there are these special points called poles and roots, and you can drop them in there and they make these force fields where they form like saddle points where they're balanced, and you can have an interaction model where I just drag this pole around, and they have like chemistry, like if I put a 0 and a pole together, they like cancel out. And so apropos of nothing, just as an abstract plaything, I've been trying to look at this for different kinds of combinatoric games or spatial games you can play with it. The other thing about it, yeah, it's gorgeous. There's lots of ways you can decorate this besides that rainbow coloring. You can do this where the size of the circles is actually telling you, it's actually I think a logarithmic derivative. But it doesn't even have to be regular. I started playing around with just stamping these on and making this, I was like, oh my God, it looks like a reptile skin, but it's organized around, like I was imagining like chameleon skin that could change color, or these like chromophores. Like there's all these decorative opportunities that like if you did contour lines for just the real values and the imaginary values, you'd always get these sort of orthogonal lines. So there's sort of a skin you could do that is some kind of like woven tapestry or something, and you can imagine you're playing with a fabric. There's also a lot of fluid dynamic metaphor. There's at least 2 different ways of looking at this in fluid dynamic terms. Like you could have flow coming out of the roots and flowing into the poles, and you can actually do a liquid motion negotiation game. So the abstractness of the underlying rule kit gives you a lot of opportunity to embellish it, I think, in a lot of ways that I think function is just being eye candy, something people actually want to touch and play with. The other thing is that, so I have a handful of ideas that involve directly manipulating this abstraction. But what I realized is that this is actually a shader program. And the expression you would write for this is actually just multipliers and adders and dividers. And when the developer I was working with proposed shaders as an objective, I was like, I don't know what shader programming is, but whatever. Like, he was enthusiastic. I could afford to be flexible. We made this whole shader game, and now I'm like, oh, that was a really lucky thing. Like, it's a testament to being a little bit open-minded about what you're doing, because now I'm like, oh, one way to look at this is as a bed of pixels with an underlying node-based programming environment. And if you got used to the heuristics of this by playing around with it, by absorbing it through interacting, and by strategizing around certain goals, then that becomes the thing you program. And this could be where you encounter the circuit system, right? Like in a lot of ways, it's like you need something to talk about. And this could be a very compelling kind of thing to describe with this. So kind of what I've done is I have about 3 or 4 game ideas that are just about directly manipulating the alien membrane. There is some version of Shaderoo, which is about programming this in a pointwise way, pixel by pixel. Ultimately, for complex analytic functions, you want to be able to take contour integrals. So I have a little thing called PathLab, which is about using a joystick metaphor to draw different paths and doing some kind of path planning or programming. And then I have about like 5 or 6 different just subjects in pure math that come up very naturally in this context, from harmonic flow to Mandelbrot sets to hyperbolic geometry. Like lots of the finer things in mathematics just live in the complex plane. So in a way, I've gone from having a pretty austere set of offerings for my game developers to now having probably more things than I'm going to be able to explore in a year. And my feeling is like only one of them really needs to work, right? I think I can take a long-term view on what I'm doing here. If we can find anything that serves as an interesting capsule game, I think that would be worth going into production on. I also have this fantasy that actually all of these are there's going to be a whole omnibus of little interactives that could coexist in one environment. And I have a very kind funder who is letting me take a kind of open mind about where this is supposed to end up. So yeah, that's the overview. I can show you some of the ideas we're thinking of, although I think everything is a little half-baked. So maybe before I show any of that, I can stop and just see if there are any questions or thoughts or feedback. Okay.
Is that I also like the idea of sort of interacting on both sides of that divide at the same time.
Yes. Yeah, you were here last year. I had this talk about learning category theory by being in dialogue with a librarian who was omniscient in one way and you were sort of pointillist in the other way. So I actually, I've had this fantasy about how this could work where at first you're playing with roots and zeros and sliding them around, and then somehow you learn that there are these pixel people living inside the screen, and each one of them lives in their pixel and just has their toolkit where they know how to, based on the instructions they've given, how to change the color of that particular pixel. So they have no idea about like the continental image on the screen, and you have no idea about the language they're using to program all of these pixels. So I'm actually hiring an artist to do sort of like an anthropological treatment. What are these pixel people like? What are their tools? What does their little station look like? And I think a really interesting game could be about the crosstalk between this high-level view and this pointwise view. I think the idea that the circuits could actually be a language that emerges as you figure out how to communicate effectively with the people who only have that pointwise point of view it's an aspiration. I'm also trying to keep everything within scope. This is the other thing where I'm like, I don't want to scare my funder by having overly elaborate ideas. But any other questions? I can show you some game premises.
There's a question on what technologies do you use to make these little games?
So I'm not a programmer. Like I've kind of taught myself JavaScript just for the purposes of prototyping. Most of the game developers I'm working with work in Unity. There's a few other game engines, but Unity seems to be the kind of state of the art among indie game developers. So yeah.
How many lines of code is one of these things in Unity?
Well, Unity is a. The answer is I actually don't even know. Unity is it's got a graphics environment. It's got a bunch of modules that let you deal directly with sound and like coloring and all of these other things. And then there is a layer that is written in C# that does all the code stuff. To a large degree, I am outsourcing a lot of that to the game developer, so I don't have I don't have eyes directly on much of the C# code. I don't think they're that big. I mean, these were all really quick and dirty prototypes. Like even that Shaderoo game, we made that in under 3 months. and it was just one guy coding, so it can't be that much.
So would you like things where, like, if you're a little pixel guy in there, maybe different ones, like, yeah, you're either given a formula, or like maybe you're given like these 4 neighbors, their colors, and you're supposed to use that to figure out your own color? Or like, is that the sort of thing you're trying to figure out ways that give people puzzles to work on? Or
let me bring up. So there's a guy, Ricky Rooser, who has made an exquisitely well-designed complex function plotter. So like the simplest thing is like if I z minus a, where a is a mutable, that draggable point is a. From an interactivity side, if I grab this and drag a around, I can essentially I'm dragging a root. But from the standpoint of these pixel people living inside of each of these pixels, they've been given take your coordinate z and subtract whatever the user has positioned a to be. So if I move a from there to there, the pixel person living in that pixel was previously, his value was equal to a, and now it's going to be something different. Whereas this person over here, their updated display is going to be their value subtracted to a, and if the user has, I haven't really described this out loud before. But do you see what I'm saying? Like there truly are 2 equally effective ways of looking at what's on screen here, either from the standpoint of the generic instructions that all of these individuals get, subject to mutable variables that the programmer, can control.
I guess I was thinking of like this is cellular automaton version where like you don't have this global formula. You just know I'm going to do whatever my neighbors. I'm going to take their values and I'm going to like update based on what they're doing.
That's interesting. Yeah, right.
From the same perspective.
Well,
you don't have to know that,
yeah, it's a funny thing with shader programming. Part of the idea with shaders is that they are memoryless and blind. Like each pixel doesn't remember what it was doing before and can't see its neighbors. But then you can do things with buffers that allow you to implement cellular automata using a shader. So we've talked about that a little bit. One of the interesting things is you can also take this, you can take some image, imagine a complex function here, and you can either take its derivative or take its antiderivative. And that has some pretty interesting rules, right? If all of your zeros, all of your simple roots disappear, all of your saddle points become roots, and all of the poles become double poles, or they increase by 1. So if you wanted to explain how that's happening from the standpoint of these pixel people, they would actually need to, the pixel person is seeing some, yes, I feel like this might need to wait for illustrations. Basically, if you live inside a pixel and you're looking at a complex value like this yellow, which has an argument and a magnitude, and you look at how it's changing, right? Like how scaled is it from what it should be, and how rotated is it from what it should be? If you express that as a complex number and then light up your pixel that color, and you all do that, you're going to generate the derivative of this function. So that's an example where the logic being used by the pixel people is utterly distinct from the logic of the person strategically using differentiation to achieve some goal. But it does require them to have a little bit more consciousness of what's around the value they're looking at, not just the value itself. So that's at least one place where, like considering the extenuating circumstances around a point is probably something the pixel people are going to have to learn to do in this game if it's going to work. So, I don't know. Does that make enough sense? Okay.
So, Paul, how would you see high school students using it?
Yeah, so this is, when it was more explicitly about number questions, it was a little easier to think about where in the curriculum this could line up. I think this is another lucky liberty that I have at the moment is that I don't think we're super strict about what the specific audience or what the segmented demographic this is for. And I think in the end it might be that the community of people who like these sort of thinky puzzle games becomes the first hot core audience, and it's whatever its educational value is maybe something that can come later. But we do have that flexibility. So I think it's like figuring out what can work and then organizing it around and marketing it to the appropriate audience. Like a lot of the games I showed you, some of those could be played by elementary school kids, and some of those really are probably not for anyone in high school. You know, you get a range of levels of challenge with these. So the answer is I don't know. It is.
Sort of along the same lines, so you mentioned that this Dragon box has sort of problems of transferability.
That's, yeah, so there aren't, as far as I know, there haven't been that many studies, but that seems to be the initial result from that.
And so I'm wondering if you sort of have thoughts about how you might, and I guess maybe I'll just throw it out there. So it seems like if you could develop the tools sort of through this interactive medium, then applications might be the sort of final levels, where sort of once you have some intuitive grasp of how the complex numbers work, then maybe you introduce something about their role in quantum mechanics.
Yeah.
And that sort of uses the same descriptions and sort of ties it into the problem that is meaningful from outside.
Yeah, I like that. Yeah, so I haven't thought too much about the quantum tie-in. There's a thing, but a lot of this is so adjacent to, you know, like harmonic, like irrotational, non-compressible flow is like every complex function involves two such harmonic flows. Mobius transformations are isomorphic with Lorentz transformations. There's a special relativity tie-in. So yeah, like terrestrializing it in terms of actual physical theories seems like one way to do it. The other thing I was thinking about is that, like, on some level you maybe first encounter this node system as a way of programming images, but this is where numbers come in, right? It's here that you're going to need to refer to the coordinates and the colors, and then at some point you can actually forget all about the complex numbers and really just use this to make a Celsius to Fahrenheit converter or whatever else you'd want to do with numbers. But you've encountered it with the full power of this reversibility of you know, differentiation and integration if that ends up being part of the game. But yeah, it's like the image to me, yeah, is telling the story in the opposite direction, and then where you end up is that you have a tool that can be applied in all of these different ways. Actually, before we run out of time, I do want to say one thing, which is, you know, as a kind of self-taught category theory fan, I have this thing where I say I feel like I'm seeing ghosts. You know, like I'm like, there is something about taking the derivative of a function where it's sort of a forgetful action, and then when you take the antiderivative, you don't just get a single function, you get a complex numbers worth of functions indexed by the additive constant, and that's an inverting, like there's something that feels very adjointy or monadic to me about this. And every so often I'll come across, like, this is from Paolo Perone's notes on category theory, where he says this exact thing. The complex logarithm is, it's not a function, it's actually a co-Kleisli morphism based on the universal covering comonad. But it's like, this is all I can find, right? It's this one paragraph. And I'm not, you know, I'm not strong in terms of thinking about this stuff, but I'm extremely interested in and actively investigating complex analytic functions. So one thing I could throw out to the group, if anyone can help me flesh out a sort of categorical point of view on what's here, I feel like that perspective might be very helpful for the purposes of exploration. Like, I mean, the ingredients here are fundamentally adders, multipliers, and exponentiators, and all of their inverses. So to me, I'm like, well, that sounds an awful lot like a closed Cartesian category. And I'm like, are any of the goodies associated with closed Cartesian categories like available here in some way?
What sounds like a closed Cartesian category?
It's products, coproducts, and exponentials.
Is what you have
right. So the fundamental ingredients in both of these are adders, multipliers, and exponents. And I don't have the exponent built in this one, but those, like, from the beginning, those turned out to be all I needed to do complex analytic functions in general. But like I have not succeeded in figuring out for myself whether there are underlying objects and morphisms or something that can anchor my, you know, that hunch. So anyway, that's not an explicit question. It's just saying that I imagine there's probably a cool categorical point of view here, at least somewhere, and I'd love to chat with anyone who thinks they can help me think that through.
This is a slightly different direction, but your node-based programming environment, your reversible node-based programming environment reminded me a lot of like string diagrams and rel category of relations. I don't know if that triggers anything for you, but that's definitely something to look at if you want to think about sort of that category theory perspective on those sort of pictures. So.
Yeah. So yeah, this is the question. Like, what you're doing is you're reversing the dependency between different, the different fields in the data layer. And I'm curious, like, yeah, are there any string diagram paradigms where that idea of
you can
What you did for
normally read
reglog,
from top
Huh?
to bottom.
what you did for reglog
was
was,
reglog reversible, or?
yeah, they were just relations. So, yeah.
So like a string diagram, you can read from top to bottom like normal, but in relation, you can also read it from bottom to top just as well, because it's relations.
Right, and that was, I mean, relation.
That's almost like what you were doing in that example about the turnaround.
Except yours are reversible in the sense that like there's a single answer,
Yeah, well,
but
that's
not a set of answers.
Yeah.
Well, no.
Only because that example was right.
But I think you probably want
But it is, so first, no. So relational programming was something that I definitely like looked at like, I mean, it was one of the main inspirations for this. I will say that like, something to say is that you really need to be using complex numbers because you can ask a question that has multiple answers. Like if I build a square rooter and I say, what's the square root of 9? It's set up in a way where it can only show me either 3 or -3, but not both at once. But what's really beautiful about the complex numbers is that there's a path, there's a statefulness to it that allows me to manipulate it in a way that I can change over to the -3 and back to the 3. And that, again, that feels like, at any rate, it feels that the complex number system almost wants to be a relational query language for numbers, like affords this interaction model that allows you to cycle through solution sets in an interesting way. Again, I don't know, that doesn't fit well in a talk of this sort, but it is like the main thing that got me excited about this when I was first thinking about them.
So what happens if you go through a root?
If you go through a root?
Yeah.
What do you mean?
If you go through 0.
I can literally show, let's find out.
Like yeah, if you have something that does a square root, and then you take the thing that you're square rooting through 0.
Yeah, okay, so this is a multiplier in the complex plane. So this is some complex number, this is some complex number, this is their product. And the geometric rule is that this angle added to this angle is the red line, and this length times this length is this length. So what I can do with this is if I, so if I restrict myself to the real line, it's like, yes, 2 times 3 is 6. To make a square rooter, I can bind these. And now I can say, okay, 3 squared is 9. And then I can actually reverse, well, and something to say is that what that means is that this angle is always twice what this orange angle is. So I can, if I chase this around, the red one is circulating twice as fast as the orange one. I can pass control to this one, and now it's a square rooter, right? Square root of 9 is 3. But -3 is also a legal solution, and I can get to that one by going around like this. And by the time I've gotten back to 9, I've only dragged this halfway around. If I go through 0, they both just land on 0, basically.
Well, but I guess you never get to exactly 0. But like in theory,
yeah. Okay. So so yes.
Right.
So yeah, you can do stuff like solve for x equals x plus 1, and like there are cases like that where yeah, infinity or dividing by 0 are sort of these bad edge cases. But a lot of the more conventional bad cases actually get very nicely resolved by the complex numbers, and then.
If you try to wiggle it right around 0, you might see chaotic stuff or something. You know, or maybe I'm being really dumb.
Oh yeah, no, you can break it. Look, it's stuck.
Okay, great.
Yeah.
Something to happen.
But and this is, we know that happens. That's actually a special mode. Like it knows yeah, what is it? We call it collapsed.
Yeah.
You can hit collapse states and then you just have a broken node sitting in the middle. So yeah, how to patch up those last holes is one of the several open. No.
I feel like you're saying there is no way.
Yeah.
Yeah, which is kind of a bad news for compositionality, right? If you've got a really big thing and something drifts right into 0 and the whole thing breaks.
Well, I mean, one way to do it would be to like treat it as a multifunction.
Mm-hmm.
and then you always have two solutions.
Mm. Yeah, well,
and then when you go through 0, both the solutions become 0. But the problem is that when you go through 0 and then you leave 0, you don't know which solution to do. But if you have both, then there's no problem.
Yeah, this is one where I can pull out an adder, make sure the 2 points of the adder add up to 0, and then bind this to my square root. And now I've made a full square rooter where I can see both square roots at the same time. And this is
there an anomaly still if you try to wiggle around 0?
Yeah, they're both going to get stuck there. And that's like, and again,
I didn't know which one to be.
Right.
yeah, it's yes. So there are there's a lot of interest and a lot of problems yet to be solved. Yeah. Yeah, and that's, you know, it's there's a lot that emerges when you get to play with it from this angle. Like, this is part of the kind of hidden joy of this, is that getting over the abstraction barrier is kind of a nightmare with people, but then a lot of very familiar things, like all the identities, like the commutative property of addition is just a statement that parallelograms are symmetrical, but like the associative property is just the fact that you can project movable projections of cubes into the, like the distributive property is like a scalable, every identity is now not something you have to have memorized. It is an apparent feature of this environment, and each one is a geometric construction. So it's a great little exercise to sit down with this and build out all of the different identities. Like, everything you're familiar with shows up in a slightly different modality. And there's a lot of just charming little things about this system that I was excited about, but I think, you know, hard to gamify, as it turns out.
I guess my role in this presentation has been to nitpick.
Yeah. Oh, do you have further nitpicks, or?
No.
Oh, okay.
I mean, this seems like it could be a good pedagogical tool for teaching about numbers, complex numbers.
Here's, so there's, so Brilliant.org was kind of a soft partner on this grant for a little while. So they have an online educational course that is to some degree aimed at adult learners. So I had tried to develop a Brilliant style, and it's all like interactives with multi-choice answers. And I really tried to develop, a curriculum for this that sort of introduced this and also, you know, showcased a lot of what the interesting constructions were. And what I found is that it really didn't work that well because this is an abstraction, right? It's not like a visualization is something that makes the concepts clearer, and this isn't that. If you've piled up enough things, this gets extremely confusing. And so it was very hard to simultaneously try and teach the concepts of complex numbers and show off this. Like, I was optimistic that it would be an interesting basis for an online course, and I wasn't trying to make it. I was really miserable because I could sense that this wasn't that edifying.
I could imagine you could like say, I want to nickname this A plus B, and once I nickname it, I'm allowed to like make the stuff that made it A plus B fade into black or something.
It's,
and then you could like start to let the user get rid of the information that was redundant or like hurting their eyesight.
yeah, being able to hide intermediate layers. The other thing, in a funny way.
It's like the operatic point of view too. Is like you want a gray box or black
Yeah,
box
yeah.
that you've already used to create the thing, and if someone wants to zoom in and understand where it came from, they can.
Yeah,
You
yeah.
can also put it up in.
I think that's super critical. The other thing that's missing, and I mentioned it verbally, but yeah, you really don't want all of your spaghetti all at once, right? You want to be able to box up a circuit with and decide what's going to be available from the inside or outside, which I think is very operad-like. So that capability just isn't here yet. The other thing that actually is great about these, I mentioned these are based on the same underlying data structure, like getting that reversibility working. We only had to do it once, and these are just two interfaces on the front end of that. But like, what's confusing about this is that it becomes a big visual mess, and also the levels of scale are all over the place. Like, if you multiply 20 times 30, your answer is like 5 feet over there. So it's very easy to lose track of things. But it has all of the geometric intuition you'd need to understand why, you know, e to the x times e to the y is e to the x plus y. This, on the other hand, almost is a perfect complement to that. Now all of your numbers are fixed in place, you know where they are, and you can see the schematic relationship between all of the pieces. So I do have a thought that maybe the final version of this as a tool is actually a paired programming environment, where this is where you set up the schematics, and this is where you kind of do the semantic reasoning about why things are moving or positioning themselves.